In this video, we're going to go over how to search a binary search tree. So first, let's review binary search trees. Remember that a binary search tree is a type of tree that has two conditions. One is that every node only has one parent, and every node only has, at most, two children. The second condition is that you take any node in the binary search tree and all of the nodes underneath it to the left are greater than it, and all the nodes underneath it and to the right are less than it. So those are the two features of a binary search tree that must be true in order for any of the algorithms that we talk about going forward are true. We have built we are going to be building a binary search tree class to kind of show you how you can work with a binary search tree. And so the class is called binary search tree. It is, in this case, we're going to use integers, but the class is templated. And as we talked about last time, trees are built based off of how the nodes are inserted in what order. So in this case, we've put 22 in first, so it is the root node, then 11, which is going to go to the left, and then 49, that's going to go to the right, and then the rest of the tree is built based off of those insert. What's going on behind the scenes is that you have two things you're keeping track of: the size of the tree and the root node of the tree. Those are part of the private member variables, and the struct is set up as a private member struct called node, and that is just like a linked list. It's going to keep track of the data as well as the two pointers that can go to the two children. The constructor is just going to set up the initialization of the two private member variables, so setting the root to null and the size to 0. So we're going to go through how to search, and one of the really nice things about binary search tree algorithms is that they're very intuitive. It's exactly what you would do if you knew this about a tree. So if you were told that those two conditions were true for a tree and you were asked to search for 40, what would you do? Go ahead and try it out yourself. Pause the video and trace out the path, highlighting the edges and circling the nodes visited to see if you got it. And then come back and we'll do it together. Okay, so we start at 22, so we're going to visit 22 first because it's the root, and then we compare. So 40 is greater than 22, so we know that 40 is going to be somewhere on the right of the tree. So we're going to go to the next node, which is 49. So we know 49 is, or 40 is less than 49, which means we need to go left. So we're going to make our way to 35. 40 is greater than 35, so we're going to go right. And then 40 is less than 41, but we can see that there are no children to 41. So when we go left, we're going to get to a null pointer. So that's an important feature about any tree, is that, and we don't usually draw these because it gets kind of cumbersome, but it's really nice to draw them when you're writing out your algorithms. But all of the leaves have two children because they're all structured with a node, and those two children are going to have initialized values of null pointers, those the leaves children. So here we searched and we got to a null pointer, and so we know that 40 is not in our tree because we reached a null pointer. So think about it. How do we search? What's the best coding pattern for searching a tree? What do you need to be thinking about in order to write this algorithm? So go ahead and pause the video and think about these different options, and then we'll go through them. Okay, so the first option is just use one pointer, loop until you either find what you're looking for or you hit a null pointer. Second option is, like many of the things with linked list, you're going to have to keep track of a prev and a cur pointer. Same idea though, loop until found, and then or loop until you get a null pointer. Loop by advancing the root pointer until found, or a null pointer, and then recursion, something with recursion. So let's rule out this one. Once you find where it needs to be inserted, you're only connecting it to that point itself, right? So if we were looking for 19, we would find 19, right? If we were looking for 40, we would get to a null pointer. So in both of those cases, you actually don't need any information about above the node that you found. In this case, you have nothing to do. And then in this case, you just need to link it to 19 itself. So you don't need to keep track of 2 pointers. This is also not a good idea. You generally, just with linked list, you want to always make a copy of the pointer, so the head node or the root node, because you don't want to move the root node around, and you don't want to move the head node around, because then you've lost the front of your linked structure. Recursion is an option, and trees are very recursive, and so we'll look at that. But we're going to go with this coding pattern, where you keep track of a cur pointer and you loop until you either find what you're looking for or you find a null pointer. So this is what this algorithm looks like. So first you need to make a copy of the root. So just create another pointer. It's going to be a node pointer. And use a good variable name. Common variable names are cur, current, node, or something like that to indicate that it's something that's changing through an iterative algorithm. Loop until you find a null pointer. So you definitely have to end once you've hit a null pointer, right? Otherwise you'll have problems trying to go somewhere that doesn't exist. And then, as we talked about, you're just going to keep checking the value, which in our node is called key, and see if it matches whatever you're looking for. And remember, this is a templated class, which we've talked about, which means that this class will work for any tree type. It could be integers, it could be strings. And if you have found it, then you're going to return true. Otherwise, you're just going to either go left or right. So if you're at a particular node, so if we start at 22 and you're looking for 40, if the key is less than 22, then you're going to go left. If the key is that you're looking for 40 is greater than 22, which it is, you're going to go right. And you're going to keep doing that until you either hit a null pointer or until you find, and then this will break out of the loop by returning out of the function. If you get all the way through and you eventually hit a null pointer, that means you didn't find it, and so you're going to return false from the function. So this is the iterative form of search. It's almost exactly like iterating through a linked list. There's like really nothing different other than you make this decision, right? You are choosing to go right or left instead of just choosing to go to the next node. So recursion is an option, and so let's look at the recursive solution for this. So the recursive solution is first going to require a helper function, which recursive functions often need. And to write the recursive function, a common syntax for recursive algorithms is that the function that is the helper function, so it's not the original function called, you just put a underscore in front of it. There is also a pretty common technique to just write the word helper, so use the same name but put search helper. So the helper function takes in a node and a key. So we want to start at the root node for the recursive search, so we're going to send in the root. And so this is the same idea as making that copy of the root that we did in the iterative solution. So root's getting passed in, and now we have a local copy of it inside of the recursive call. Just as before, inside of our loop, we broke out anytime we found it. We need to find a way to break out of our recursive calls, right? So our base case in this case is as soon as we've hit a null pointer, we're done. We know that we have not found anything. And then, as before, the other kind of way that we know that we found something is if the key that we're searching for matches the value that's stored in the struct. So we're just going to do the same thing we did in the loop. We're going to check if it's equal. We're going to check if it's less than. And if it's less than, we're just going to send in the left node into the recursive call. And if it's greater than, we're going to send in the right node to the recursive call. And so this has that same iterative feature, it's just doing it recursively. So instead of having a loop that resets the cur value, we're just sending that cur value in recursively, and so it becomes cur. So it's the same thing. Recursively sending in cur to the left is the same as iteratively setting cur equal to cur to the left. So you do want to be careful about recursive functions always, because they do have the overhead of the stack that's getting created. So while it's often sort of a nice solution, and it's also for some people very intuitive to be thinking about writing code recursively, you do have to be aware that there is that overhead with recursive algorithms that you sometimes want to be careful about. One thing that's nice versus a linked list, which was had a lot of restrictions to recursive algorithms because your recursive calls are as long as your linked list is. The nice thing about trees is our recursive stacks that are getting built are only going to be log n, right? So you're only going and checking the height of the tree rather than all the elements of the tree. So that's nice. All right, so that is it for how to search a binary search tree and what that algorithm looks like.